This talk is about computing shortest paths from a single source in the CONGEST model of digital computing. We start this talk by reviewing the computational model that we are going to use, the problem that we are trying to solve, and later we'll present our result. Okay, so in this lecture we focus on telecommunication networks, which, as most of you probably know, are collections of devices such as computers or cell phones that are connected together in some way and can exchange messages via these connections. It's quite natural to model such a network by an unweighted graph, as we can see for example here. Each vertex in this graph corresponds to a device in this network, and each edge indicates that there is a connection between them. A device in this network can communicate with its neighbors by sending messages along these edges, where the exact way in which this communication is done has of course to be determined. So in this lecture we are going to use the standard CONGEST model of digital computing, in which we assume that communication is done in synchronous manner. That is, we assume that all devices wake up in the same time and that they proceed to communicate in discrete rounds. In each such round, each vertex first receives the messages that were sent to it in the previous round, if there were any, performs some internal computation, and then sends possibly different messages to all of its neighbors, where the size of these messages is bounded from above by an order of log n bits, where n is the number of vertices in this network. We usually assume that each vertex has a unique identifier that can be represented using an order of log n bits, and that initially each of them only knows its own identifier and identifiers of its neighbors. However, in some cases, these vertices may be provided with some more initial information. For example, these edges may have weights and or directions, and so the vertices in such cases will also have to know the direction or the weights of their incident edges. But it should be emphasized that this information does not affect the communication in any way. That is, the communication is always done in a bidirectional manner and always in discrete rounds. This is just an input for the network. Now, in many applications, these vertices would like to compute some properties of their own network. An important example is the single source shortest path problem, in which we have a single designated vertex S, which we call the source, and each vertex wants to compute its distance from the source. Of course, taking into account the weights or the directions of the edges, if such are given. So we would like in this case to devise an algorithm or a protocol that each vertex is going to execute in parallel, so that by the end of the computation each of them will know its distance from the source. Such an algorithm is called the distributed algorithm, and of course our goal is to find the fastest possible algorithm, where in this model the complexity is measured by the number of communication rounds that it requires in the worst case. Okay, now we are almost ready to discuss the results, but before that we have to introduce another important parameter, which we denote by d, and this is simply the diameter of the network itself, ignoring the weights and on the directions of the edges, again if such are given. This parameter is important as it characterizes the complexity of many problems in this model. For example, it is very easy to show that omega d is the lower bound for the SSSP problem, and that for undirected unweighted graphs this lower bound can be easily matched by performing a standard BFS. So this is a trivial case, but things are getting more interesting when these edges have weights and or directions. For example, for directed graphs, a standard BFS here may take an order of n rounds, even when the diameter of the network itself is much smaller. On the other hand, an order of n rounds is always enough to solve the SSP problem for weighted and directed graphs by using the standard Bellman-Ford algorithm. So this brings us to the following inter-string gap. On one side we have this trivial lower bound of D, and on the other side we have this almost trivial upper bound of n. And closing this gap is an important problem in this field. Previous works have managed to make some progress. First, a stronger lower bound of almost square root of n was shown in this work. Second, the upper bound for this problem has been improved in a series of works, starting with that of Elkin, which works for weighted and undirected graphs, and finally getting to this bound, which works for weighted directed graphs with non-negative integer weights. For small values of D, this bound is very close to the lower bound, but for larger value it is still far away. We managed to improve this bound by devising a new randomized algorithm for solving the SSP problem for the same class of graphs that uses no more than this number of rounds. And in the rest of this talk we are going to explain in a very high level how this result was obtained. We start by considering a slightly different setting in which we want to compute distances in overlay networks, which is an interesting task by itself. An overlay network is essentially a virtual network which is built on top of another network. That is, the vertices of such a network are some subset of the underlying network vertices, and its edges are some set of virtual links between them. For example, on top of this network, a possible virtual network can be something like this. So suppose that we have a weighted directed virtual network whose minimum edge weight is some positive integer m, and assume that our goal here is to compute distances from a given source up to depth d. A possible way to do this follows from the following observation. Let us first divide the nodes of this network into several layers according to their distance from the source, where the ith layer contains all the nodes whose distance belongs to this range. Let us look at some node v that belong to some layer I, and consider some shortest paths from S to it, as we can see here. Note that since v belongs to a positive layer, its distance from the source must be greater than 0, and so there must be a vertex x that precedes it in this path, as we can see here. Now the weight of this edge must be at least m, as m is the minimal edge weight. And on the other hand, the weight of this path is at most im, as v belongs to the ith layer. This means that the weight of this subpath is at most im minus m, or in other words, this means that v must have an ingoing neighbor x that belongs to a lower layer, such that its distance from the source, together with the weight of this edge, is equal to the distance of v from this source, as we can see here. And in fact, it's easy to show that x is actually the vertex that brings this to the minimum. And so this means that we can compute these distances iteratively layer after layer. More explicitly, each vertex is going to maintain a set of announced vertices, which initially only contains s, and then we perform a series of updates, where in each such update we compute the distances of the vertices that belong to the next layer until we reach the required depth. In more details, in the ith update, each vertex whose distance have not been set yet checks whether it has an ingoing edge from a previously announced node x, such that this condition holds. If this is indeed the case, then V must belong to the ith layer, and so we can update its distance accordingly and announce it. To analyze the running time of this algorithm, we know that it is essentially performs D divided by M phases, where in each phase we only have to broadcast the distances of the vertices that were updated. We know that we can broadcast M tokens using an order of M plus D rounds, where D is the diameter of the underlying network. And so if we denote by Mi the number of vertices that were updated in the ith phase, we get that the total number of rounds is equal to this bound. As each vertex is updated only once, this sum can be at most the number of vertices, and so this gives us the following bound on the running time. And it is also possible to generalize this procedure to compute distances from a set of sources, which would increase the running time to this bound. We are going to use this procedure to compute distances in general networks, and we are going to start with the case of unweighted directed graphs, as it is slightly simpler. The approach is pretty simple and follows the same framework that was used in the previous works. Instead of running a BFS from one node, which may take too many rounds, we select a set of sources and export the graph in parallel for all of them. Specifically, we choose a set of roughly n divided by edge vertices that consists of the source vertex S and contains at least one vertex on one of the shortest paths between every pair of vertices whose distance is equal to edge minus 1. Such a set can easily constructed in a constant number of rounds with high probability by simply sampling these vertices. Next, we are going to perform in parallel an outgoing BFS from every vertex in S up to roughly depth h. And then we construct an overlay network edge over this set S by adding an edge from x to y if their computed distance is at least h. And then we set its weight accordingly. The main observation here is that the distance of every vertex V from the source S is equal to the minimum of this set of values. To see this, let us fix some shortest path from S to V in G and divide this path into a sequence of consecutive paths of edge vertices each, as we can see here. By the way we choose the set S, we can assume that each of these paths contains a vertex from S. And so by only considering the vertices that belong to every second path, we get that edge must contain a path to some vertex x such that this equal to the distance of V from the source. So we have an overlay network in which the minimum edge weight is at least h, and we want to compute distances from S. For this we can use the previous procedure, or we can even do better by repeating this scheme again on edge. That is, we can sample another set of vertices and compute distances from them and so on. By choosing the parameters correctly, we can get the following running time. We move now to the weighted case, and we follow the work of Froster and Nanogake. First, by non-reduction, it's enough to devise an efficient algorithm for computing distance estimation, which are 1/2 approximation, and preserve a certain form of the triangle inequality for the graph's edges. To obtain this, they use a similar framework to the one that we use in the unweighted case, and this goes as follows. First they constructed a set of skeleton nodes, computed an approximate edge hop distance from every such node, and constructed an overlay network on top of them. Next, they computed distances from S in edge, and constructed the unweighted graph G' by multiplying the weight of each edge by 2 and adding the shortcuts from the previous step. We can show that the distances in this graph are two approximations to the original distances, and that for every vertex there is a shortest path that consists of at most edges. This means that to compute the required estimations, it's enough to compute distances in G' up to edge hops, as then the triangle inequality for the edges will essentially follow from the fact that the distance metric on G' obeys the triangle inequality. In the previous work, the step of computing distances in edge required too many rounds. So in this work we devised a faster method to compute approximate distances in edge that preserve a certain form of the triangle inequality, which will be sufficient in our case. In a very high level, we achieved this by devising a new weight modifying technique. Recall that in the standard rounding technique, we perform an order of log n w iterations, where w is the maximum edge weight. And in each such iteration, we change the weight of each edge to be the maximum of these two values. And then we compute distances up to depth 2 to the I in this graph. And at the end, we set the final estimation of each vertex to be the minimum taken over all these estimations. This gives us edge hop epsilon plus 1 approximation to the distances, as the ith iteration gives a good approximation to the vertices whose distance is between 2 to the I minus 1 and 2 to the I. The problem with this approach is that this rounding does not necessarily preserve the triangle inequality for the edges. For example, we may have a path in which the weight of all the edges except the last one are relatively very big, while the weight of this large edge is much smaller. So we can get an estimation only at high iterations. But in such iterations, the weight of this large edge may increase by a lot. And so the triangle inequality will never hold. To fix this, we introduce the iterative gradual rounding technique. We essentially do the same thing, but now we set the weight of each edge to be roughly this. That is, we multiply the weights here by some factor, as you can see here. And we also add the estimations from the previous iteration as shortcut edges. As estimation now, we take the weight of the lightest path that consists of possibly one shortcut edge, together with the path of weight at most 2 to the I. So why the triangle inequality holds now? Let us fix some edge xy and consider the path in edge that led to the final estimation of x from S. That is, the final estimation is equal to the weight of some path in edge 1 that possibly start with a shortcut, and this shortcut corresponds to a path in edge 2 with another shortcut, and so on. So by unfolding all these shortcuts, we get this path from S to x, as we can see here, and we add to it the edge xy. Note that the vertices z1, z2, and so on are actually the vertices to which the shortcut edges were connected in the corresponding iterations. Now we can find an index I such that the weight in edge of this subpath is at most 2 to the I plus 1, and the weight of this subpath is at least 2 to the I. Note that in the ith iteration we must consider this subpath, and so the estimation can be at most the weight of this shortcut plus the weight of this path in the graph edge I plus 1, which can be at most this value. Now, as this path is at least 2 to the I, this additive term can be summed by a multiplying factor of this term, which gives us the following bound. As we also multiply the weight in each iteration by another such factor, the estimation for x must be at least the weight of this shortcut plus all these terms. And so we get that this inequality must hold. In conclusion, we have reviewed in this talk the current state of the art for the SSP problem. There are two important problems that are worth to consider here. The first one is to close the remaining gap, and the second is to check whether these new techniques can be used to solve other problems or to improve the algorithms for the SSP problem in other models. Thank you for listening.